Hi everyone, welcome to today's coding session. Today I'll be solving the merge interval problem using Python. I will explain the problem is constrained two approaches, a brute force solution and an optimized two-pointer approach. As I code, I'll explain each step in detail. Near the end, I will compare time and space complexity analysis. Let's get started. So understanding the problem, we will be solving the following problem. We are given an array of interval where each interval is represented as start here and as endᵢ. Our task is to merge all overlapping interval so that there are no two overlapping interval in the output. After processing, we return a list of non-overlapping interval that cover all the intervals in the input. So for example 1, we are given this interval 1, 3, 2, 6, 8, 10, 15, 18. Our output is going to be 1, 6. And as you can see, what's happening here is we're merging these two together because there's an overlap between 3 and 2. And this is explained here. Then for example 2, we got 1, 4 and 4, 5. So as we can see, 4 and 4 are the same. So here we know that 3 is greater than 2, but here 4 and 4 are the same. So whether it's greater than or equal to, we know that we're going to have to merge them together. And that's the explanation for that. So now that we understand the problem, let's think about the constraint. So here, we know that interval could be very short, 1 interval, or very long, 10,000 interval. Since we must process our interval efficiently, we should aim for an O or big O of n log n solution, as sorting is required or will be required for this. And each interval consists of exactly 2 elements, is what this is telling you here. A start and an end element, ensuring interval length equals 2. And startᵢ here is always going to be less than endᵢ. It's going to be startᵢ being as low as 0, but as high as 10,000. The input intervals are not necessarily sorted, so we must sort them based on start time before merging. We must preserve the order of non-overlapping interval after merging. So these are key takeaway. From these constraints, we can conclude that efficiency matters since intervals can be large, up to 10,000 interval. And a big O and log n solution is ideal since sorting is necessary before merging. And an in-place approach is beneficial to minimize extra space usage. So a sorted approach is promising because intervals are easier to merge when processed sequentially, ensuring efficiency, merging in a single pass after sorting. Now that we understand the problem, let's think about how to solve it. First, we'll try the brute force approach, then optimize it with a more efficient solution. One approach is to iterate through intervals, sort them by start time, and process them sequentially. If 2 intervals overlap, we merge them into a single interval by updating the end time. Otherwise, we add the current interval to the result list. So here is an example, which we'll walk through, which is example 1. So thinking through it, what we're going to do here is we're going to sort first the array. The reason we're sorting, you would think, is redundant because they're already in order, is because there may be a situation where they're not, which I'll give you an example later for that one. But either way, it's going to be sorted. Now, the first interval, which is 1, 3 here. So let's just take them both out since we already know. And then we got 2, 6. These two overlap. We know that 3 is going to be greater than or equal to 2. Since they overlap, what we're going to do is we're going to create one list. So we have only one range. But before we do that, what we want to make sure, before we end up doing that, we first compare this and this, and we know that it's true, that this one is greater than 2. So now we know the overlap, but now we want to know if we're going to end up having this end. In order to figure that out, now we're going to again compare 3 against, or another way of doing it is we can assign, let's say we have max now. So we're going to get the max of 3 and 6. And we're going to assign that to interval equal, or intervals. And since we're looking at index 1, and we have, again, it's going to be the end. So this will be the first interval, and this will be the end time. So now, whichever one's greater, which in this case we know 6 is greater, is going to be assigned, and it's going to create this, where we got 1 and 6, and that's what we got, the merging here. So now we're going to do the same thing, but we're going to do it for the other ones, for the remainder. So now we're going to ask the question, so we got 1 and 3, and we compared it to this. So now we're going to say, is 1 and 6, compare it to 8 and 10. So now we're going to say, is 6 greater than or equal to 8? And that's false. So now, since that's the case, we're going to update this. Then we're going to have 1, 3, actually no, 1, 6, and then we're going to have 8, 10. And then the question will come about again here, where we're going to ask, okay, where is this? So we got 8, 10, so 8, 10 here. Is 10 greater than or equal to 15? And we know that that's false. So finally, what we're going to do is we're going to update this. And we're going to get 15 . So now we got 1, 6, 8, 10, 15, 18. And this will remain as such. So the one thing I did forget to do is that we're going to keep track. We want to keep 2 type of trackers. So one is going to be index equals 0. And that's just going to keep all the original ones based on the fact that they're in the proper range. And then we're going to have I, which is going to be used as a scanner, which we're going to initialize to 1 for scanning. So now, again, we had here is 3 greater than or equal to 2. Here, since we're using index, we're comparing intervals, and we're going to say index in this case, since we already know that's already equal to 0. And this is going to be 1. It's always going to be 1. And the reason for that is because we're comparing the end time. And that's where we get the other part of the expression where we say, is it greater than or equal to 2, which now we're going to use integral again. And we're going to compare it to, so now we are at position 1, which I is going to be position 1, which is where it starts. And now this is going to be at position 0. So now that's how we compare it to the 2. And as we saw, 3 is greater than 2. So what we're going to have to do is we're going to have to do this max and put the higher number into the array. So now we have an updated array. And that's going to repeat through each number. And eventually, we know that we modified. So index is going to be increasing. And we know we modified 1, 2, 3. So we're going to return interval, and it's going to be up to index plus 1. So this way what we end up doing is we end up getting this modify arrayed. And this is the optimized approach I'm thinking of doing. Now, if we were not using the optimized approach, instead of comparing here and just simply bringing it back in here, what we're going to do is instead we are going to just create a list, which we call merge, an array list. And then every time we get a new one, all we do is we append it to the end. Whatever the interval is. So that's my thought process in that. And I'll show you more in the next step. So one of the things here is, as you saw, is that I ended up sorting this. So why was sorting important? The reason sorting is important is that it ensures that overlapping intervals appear consecutively, allowing them to be merged in a single pass. So now let me give you the example why that's the case. So let's say we have this situation where we got 1 and 4, and that's inside an array. And then we got 0 and 4 inside the array. So now our code will break because an edge case that we're never thinking about is comparing the first element against the first element. We're always thinking about comparing the n times. So is 4 greater than or equal to 0? And we know that 4 is greater than or equal to 0. So then if we were to follow through on this, then the next thing that we're going to do is we're going to do the max of the two elements, which is going to be 4 versus 4, which we're comparing this 4 against this 4. And the answer is just going to be 4 because at the end of the day they're the same number. So when we update this, what we're going to get as an answer is going to be this. Let's put another one. So it's going to be 1 and 4. Which would be the wrong output. So that's the reason sorting is important, because if we were to sort it, instead of having it this way, we would literally just have the correct order, which would be 0, 4, followed by 1, 4. By doing this, now we can compare, is 4 greater than 1? Greater than or equal to 1. We know that 4 is greater than or equal to 1. So now when we do max, because now we're going to compare this 4 and this 4 again, now the final output is going to give us this, and we're going to get 0 and 4. So that's the reason sorting is important. So let's implement the brute force approach first by sorting the interval and merging overlapping ones sequentially. So let's look at what the brute force looks like. First step, right off the bat, we're going to sort. And this part of the code here, what we're doing here, particularly where it says here x equals or x index 0, this right here is showing that we're indexing based on the first element, which is the start time. Which, if I was to write, this is an anonymous expression, and if I wanted to do the same thing, I could do it this way, which would be, let's just call it I in intervals. And then when I look at I, I'm looking at 0, which is going to be exactly like that, which is we know this is going to return, as we said, we have the 1, 3, for example. That's going to return the 1. And that's assuming that we have multiple array. So this is going to return this first element because the array is returning this guy first, and then we're going to get the first element. So this is doing the exact same thing, this lambda. So interval.sort lambda, and then next step is we're going to create a list in which we're going to append any new values, meaning the ones that are within the proper range. So then we're going to go for interval in intervals, and then if not merged, which is another way of saying if this list was empty, then it'll return false, and then when you put not, it's going to return true. Or merged, -1, 1 is less than interval 0. So now in this part of the code, what we're looking at is we're seeing, so now we know that the merge list is empty. So in this case, this will come true first. But if we had a merge list that was not empty, which already has some sort of elements in it, which let's say we had 1, 4 or 1, 3. Now this right here is looking at the last element, which in this case, even though there's 1, let's put 2 just to make the distinction. So now this one right here is going to look at the last element, which in this case is going to be, because we're putting 1 here, we're putting -1 here, so this is the last element in this list. And this 1 is going to give us the end time. So now I want to compare the end time with the beginning. So for the interval, in this case, so we already added this portion to the merge list. And now interval, let's say, is another number, which should be, let's make it up as I go, equal to, let's put it as 6. So it's 6 and let's say 8. So now we're comparing, is 6 less than 6? And we know that they're equal to each other, so we're going to have to merge this. So in this case, since this is false, this won't execute. This will only execute if it's true. So if it's true, like let's say it's 7, now what we're going to do is we're going to merge dot append interval. And the reason we're merging it is because the list is a unique list, it's not overlapping. So else, so the other situation is when this right here all turns out false. Now what we're going to do is we're going to merge, which will be the exact same one, the last one. And now we're going to get the max. So we already have this. And we're going to get the max of interval 1. Here we were looking at the beginning element. As we mentioned here, we were looking at this. And now here we're looking at this to see if 8 is greater than 6 or 6 greater than 8. And that number is going to be assigned to merged. So now we're going to override the current value. And then finally, when we're done, we're going to return merge. Now let's see if I made any mistakes. Interval sort, merged, intervals, merged, merged, interval, merged, interval, merged, merge, interval, and merged. Okay, so now let's see if it gives you the correct answer for the. Okay, so as you can see, it passed the test cases. Now let's see how it compares to others. Okay, so 7 milliseconds beats 96%. So as you can see, in regards to time complexity, is very good. So let me go through the code one more time, explaining what it does. For this, so the first thing we do is sort the interval, as mentioned here. Sorting ensures that the overlapping intervals are adjacent, making merging more efficient. This step arranges the interval in increasing order of their start time, ensuring that we process them in the correct sequence. This part, as I say, was looking at the start time. Next, we iterate through the sorted interval and merge overlapping ones. If the current interval does not overlap, so we're going through iterating now through all the interval. Again, if the list is empty, it's going to return false. This will make it true, and if that's the case, we're going to append the first number. So that's the first thing that we're checking. Then the second part is if merge, this portion right here, the last element of the merge list, the end time, is less than the beginning of interval, it means there is no overlap, so we add the interval as is, which is what we're doing here. Now, if this right here all turns out to be false, that means there is an overlap. And if there is an overlap, what we're going to do is we're going to find which one of the two is greater for the last two number, and then we're going to add it to the merge, so this way we remove the overlap, and then we're going to return merge. So now let's actually show a quick example of what's happening, and we're going to go back to this example, which we can just do the simple one actually. But I like this example, so I actually am going to do this one. It's a good example. Okay, so here we sorted the list. It's already sorted, looks good. Then we created the merge. Now we're looking through the interval, and the first thing that comes up is going to be 1/3. So that's the first thing we're looking at. And now that we look through the interval, it says it's not merged, which we're looking at this right here. So we know that this is already empty, so it returns false. And then not false will equal true. So right off the bat, we got merged out of pen interval. So this, on this step, now we have merged equals to this value right here. Now doing it again, we're going back to the for loop, and we're going to say for interval. So now we're doing this one. So let's move down so we can show it. Okay, so now we got 2, 6. And we're going to look at merge, and it says here, we know that it's no longer empty, so this no longer applies. And now we're looking at the last element, which in this case would be 1 and 3. And we're looking at this element right here, 3. So let's put 3 here. Is a less than, and now we're looking at interval 0, which is this guy here, 2. Is 3 less than 2? The answer is no. So this is 3 is not less than 2, so we know there's an overlap. So this is going to be false, and now we go to else. So now we're looking at, we're going to go, now we're going to try to update merge, -1 and 1. And we're going to update it based on the last element, which is -1, 1. Again. So it's max. And negative 1, 1 is 3, as it shows here, negative 1, 1. So we got 3. And then here, the difference is we're going to look at interval 1 now. And interval 1 is actually going to be 6. So which one is greater? 3 or 6? 6 is greater. So now we're working with 2 6 and 1/3. So now the list is going to be 1 6 based on that comparison. Which now that we have this is going to be updated. And now this is 1 6. And let's see, so we're here, interval. And now we're going to go back up to the interval. And let's copy this. So merge is the list is actually going to be updated because we're not, the optimized approach will do it differently. So this is going to be merged like this, and this is now going to be 1 6. So now we're back here, and we are now at 8 10. And the question is 8 10, and now we're looking at merge, which is the last element, which is 6. Is 6, the end time, less than 8? And we know that's the case, which is, this is pretty much what we were doing the comparison in. So we're going to append it right off the bat. So now when we append it, we're going to do this. Now we're going to put 8 10 here. We're going to do it one more time for the last remaining element. And now we're looking at 15 18. Is 15 18, and we already got 8 10, which is updated here. And per the code here, we're looking at the last element, and we're looking at the so this would be the last element in the merge, last element in the merge, and we're looking at the first element here, not the first element, the end time. End time is 10, and we're comparing to the beginning time here as it shows, interval 0, which would be 15. So it's 10 less than 15. That is correct. So now we're going to add 15 to the list. Now we're going to go back to the loop. We're going to X out of the loop because we went through all the elements. Now we're going to return merge. And this is the modified list that we return, which looks exactly like this: 1 6, 8 10, and 15 18. Which is why both cases are correct. So now that we've seen the brute force approach, let's talk about a much better way to solve this problem using an optimized two-pointer technique. The brute force approach appends merge intervals into a separate list, which requires extra space. The optimized approach modifies the intervals in place, eliminating the need for additional storage. We'll maintain 2 pointers, one for tracking merge intervals and the other for scanning the array. After sorting the interval based on their start time, we iterate through the list and merge overlapping interval in place, updating the existing array instead of creating a new one. So here's an example walkthrough. This is now the idea phase again, as we are using the optimized approach. So we got this, and we initialize 2-pointer. We're going to have pointer index equal to 0, and we're going to have j equal to 1. Then we're going to compare the intervals. So interval j, because now we're going to do it in place, with interval index. If interval j overlaps with interval index, we merge them by updating the end time of the interval index. And if that's not the case, then we store our next non-overlapping interval merge. So instead of creating a separate list, all we're going to be doing is just simply modifying this list. So we're going to modify this in place. And then the final output will give us that by doing this approach. That's the thought process. And the count will be 3. So we should be able to have 1, 2, and 3 all the way up to here. So before we dive into the code, let's take a moment to think about edge cases. Let's go over a few scenarios we need to handle. If interval was empty, for example, our function should simply return an empty list, since there are no interval to process. So if it's empty, we got interval. It comes out as being empty. We're going to just return this interval. Second case, if all intervals are the same, we should keep only one occurrence and remove the redundant ones. So if we get the situation where we get 2, 5, 2, 5, we're only going to return this one, and this one is going to be eliminated by modifying it in place. And the way since we have to index and index 0 is the one that tracks the unique array without overlap. This will remain the same, or will remain a 0, and therefore we're going to have this being the result. If the intervals are already non-overlapping, our function should return them without making unnecessary changes. And the only way that they are non-overlapping is now if they have unique numbers, which we can say is 6 and 8. Since they're unique, now we're just going to return the intervals as well. So it's similar kind of to the empty array, but in this case there's actually going to be value, and this one's going to be the index. It's going to be incremented to 2. 0, 1. Yep. So since it's tracking actual occurrence, it'll be 0 and 1. And then for example 1 and 2, which is what we cover a couple of times, we need to ensure that overlapping intervals are merged while maintaining orders, which is the example already showing you. Now that we thought through possible edge cases, we're ready to start coding. Next up, let's implement our optimized two-pointer approach. So let's write the code. If not intervals, we're going to return the empty list. We're going to sort it similar to brute force. And we're going to use index equals 0 as a pointer to track the last merge interval. And then we're going to use j in order to scan the array. And we're going to start that one at position 1. And we're going to go all the way up to intervals length. Now if interval index and again this is comparing the end time, if that is greater than or equal to intervals j, and that's looking at the beginning time, then we know that if this is greater than this, then we know there's an overlap. And if there is an overlap, then we're just simply going to do intervals index 1, and we're going to put the max value, which is similar to what we did for the brute force approach. So now here, so let's see, so we got index 1 and J1. The one thing I want to point out is that this one says 1 and this one says 0. This is for the beginning and this is for the end time. And now whichever one is greater between the two end time is going to be assigned to intervals. Then else, we're going to increment the index 1, which in this case we're saying there's no overlap. So this right here, we showed that there was an overlap. If this is false, that means there's no overlap, so we're going to increment the index. And then intervals index equals interval j. So here what we're doing is now we're assigning the value that we have at interval j into interval index. So that is the end time and beginning time, and 1 being assigned. And now once we're done with the loop, we're going to return intervals index plus 1. The reason we're doing plus 1 is because let's say this was just 0 really, meaning this is 0 based indexing and we were at 0 index. By putting to 1, this allows us to be able to show the list up to only 0 based index, because there's always one more, but not to include. So let's see if there's any errors here. Intervals at soar key index range 1 len intervals index intervals, and I need to put intervals there. Index intervals index interval intervals. Okay, so it looks okay now. All right, it was accepted for both cases, and let's see how it compares to others. All right, so this one's a little bit slower, but it should be the same because they're using sorting. It's the same time complexity. And now that we implemented our optimized two-pointer approach, let's go through the code line by line to understand how it works one more time. And this is a brief overview. If the list is empty, we're going to return that is empty. We're going to sort it. We're going to use this in order to find the unique non-overlapping intervals. Here we're going to use this to scan through the intervals. If the end time is greater than or equal to the beginning time of the next interval, then what we're going to do is we're going to get the max of the end time for the second interval, or this one, whichever one is max, and we're going to add it to that interval. Otherwise, if it is not overlapping with the next interval here, if it's not overlapping with it, then we're just going to increment this index, and then we're going to add that interval into index. Once we're all done with this for loop, we're going to have a unique array, which may be shorter than what we started off with, depending on the different edge cases. And now let's give a quick example to show what is actually happening now using the example. And we're going to use my favorite example here, which is example 1. So example 1, we sorted it. So this is sorted. We already went past this right here. We know that it's not empty, so it's not going to return that because it already has a value. We sorted it, then we start at index 0, and now we're scanning, starting at 1. So now let's compare the two. So we got intervals, which would be, let me just copy this. So we got interval 0, and then we got interval j, which is 1. And we know that we're working with these two guys here. Working with these two. So we are asking, which is this first guy, and the end time, is it greater than or equal to this second guy and the beginning time? Which is another way of saying is 3 greater than or equal to 2. And 3 is greater than or equal to 2. So now we're going to go to this step right here. And when we go to this step, now we're comparing again the 0 and the 1, which we know is going to be 3 for this guy, and interval 1, which in this case, we're looking at this guy now, so it's 6. Which one's greater? 6 is greater. So we're going to update this list. And it's going to be 6 now. And nothing else happens, so now we go again to the loop. Index is 0, 0 as original. And now j is going to be 2. Now the j is 2. We're going to do the same comparison. Is index 0, which is 1, 6. Where's the updated one? Okay, so we got 1, 6. So we're saying is 1, 6, and in this case we're comparing 6. And now we got, so let's put the numbers. So we got this guy, which is going to be 0, and this guy, which is going to be 2. So we know 1, 6, and 6 being the end time. And then now we're looking at 2. So we got 0, 1, 2, which is 8, 10. And we're looking at the beginning. So now we're going to compare. Is 6 greater than or equal to 8? We know that that's false. So we're just going to, now since this is false, this part's false, now we're going to go to the else portion, and we're going to increment index first. So now index is going to equal, we had 0, so now it's going to be equal to 1. Then we got interval index, which is here. And we have 1. And j we already had as 2. So what value do we have at 2? We got 8. So now interval here, we got 0, 1. So we're going to get 8. It's going to be here. And now we're going to go again on the loop. So just to make sure, we got index equals 1. We got j, now that we're in the loop, we were at 2. Now j equals 3. So in this loop, for j in the range, so now it equals 2. Now we're doing a comparison here. And we're going to say, okay, we got index 1 and interval 3. So now what is 1? So we got 1 here, 1 here. And then we got here saying 3, so we got 0, 1, 2, 3. And this. And now we're comparing 10. Is it greater than or equal to 15? And we know that 10 is less than 15. So now this interval, so this means here, since it's less than, this is going to be false. So we're actually going to go to index and we're going to increase it. So index now is going to equal to 2. And now we're back here, and now copy and paste this. So again, we got 2, and this guy is 3, which we already calculated these guys over here. And all that means is that now we're going to copy this guy, or this interval, here. So now we exhausted the list. Now we're going to return the intervals. So let's copy this. So we have interval. Last place was 2. And when we add it up, it's going to be 3. So that means it's going to go up to 2, not to include 3, when we return the interval. So when we look at this, which is what we're returning, we're going to get 0, 1, 2, not to include 3. So that's going to be the modify array that we're going to return, which is exactly what this is. 8, 10, and 15, 18. So now that we've broken down both the brute force, and let's see, because we already did the time. Yes, so we did the time. So now that we broke down both the brute force and the optimized solution, let's compare them side by side to see which one performs better. The brute force approach, I pre-did them before. So this is the brute force approach. This is the optimized approach. Because they both sort the list, as you can see here, we both sort the array. The worst case scenario, the worst runtime, is big O of n log n. When we do this here, this is going to be big O of n in worst case scenario because we go through the entire list. And the same thing here. Worst case scenario, if we go through the entire list, it's going to be big O of n. And the best case scenario is big O of k, which means we do not, or big O of index, because we do not go through the entire list, as our previous example did. So then looking at, so here, what we got for time complexity is going to be big O n log n. So now let's look at space complexity. And they both have the same time complexity. So now looking at space complexity, here for the brute force, we ended up using another array to start storing every single time we found overlap, or ones that were not overlapping. And the worst case scenario is that they're all unique and there's no overlap. And if that's true, then we're going to have big O of n that we're going to go through in regards to space. So we're going to create an extra storage of big O of n in this scenario here, if they're all unique. And now here, in this case, So now here we're looking again, looping through it. When it comes to storage, we don't have any storage. I mean, here this is being sorted, and here we're just comparing it, and then here all we're doing is again still comparing, but nowhere here are we actually creating any extra storage. All we're going to do is here we're going to modify it, and in best case scenario we're just simply going to get a smaller list, but again we're not creating any extra space. So the complexity here, the space complexity, is going to be big O of 1. So both approaches solve the problem, but the optimized solution is significantly more memory efficient because it avoids extra storage and modifies the list in place. This is why the two-pointer method is the best way to merge overlapping interval efficiently. So now, just because I like looking at it on a graph, so the brute force approach and the optimized approach in regards to time complexity is equal. The fact that you have the sorting, it's the same time complexity. Now the space complexity is where you have the difference here, the advantage when it comes to the optimized. Optimized is big O of 1, and the brute force is big O of n. So just a quick rundown. We tackled merging overlapping interval efficiently. Here's what we did. Step 1, we understood the problem. We broke down the problem statement and identified a key constraint. The goal is to merge all overlapping interval while maintaining the correct order. Second, we used the brute force approach. We sorted the interval and iterated through them, merging into a new list. The downside is that storing the merge interval in a separate list leads to big O of n space usage. And then third, we optimized two-pointer approach. Use 2 pointers to merge interval in place, modifying the original list instead of creating a new one. Same time complexity, big O of n log n due to sorting, but better space efficiency, big O of 1 space, no extra storage needed. Step 4, we compare both approaches. The brute force uses extra space for separate lists, and the optimized process interval in place, reducing memory usage while maintaining efficiency. So I hope this walkthrough helped you understand how to efficiently merge overlapping intervals. If you found this useful, don't forget to like, subscribe, and hit the notification bell for more in-depth coding and tutorial. See you in the next session. Happy coding.